Okay, in the previous video we saw that when you replace x with 2x inside the brackets of the function notation, you're performing a horizontal stretch factor a half. The graph is getting squished in towards the x-axis so that while all the y values stay the same, the x values that correspond to them get halved. Let's take a look at another example. Now, given the same parent function, we're asked to graph y is equal to f of a half x. So again, we need to take the x values that we're given here on the left of the table of values, plug them in for x, multiply them by a half, and then plug them into the function above or shown on the graph. So when x is equal to 8, we're looking for f of a half of 8, which is equal to f of a half of negative 8, which is equal to f of negative 4, which is equal to 0 from above. When x is equal to negative 4, we're looking for f of a half of negative 4, which is equal to f of negative 2, and from above that's negative 4. Now I've got negative 2 here because it was one of the x values in our original function, and if we were to have that, we'd get negative 1, and we could look up f of negative 1 from the table, from the graph, but I'm going to skip that one because it's not one of the 5 main points that we've got outlined in red. And similarly, I'll skip this line here with x is equal to 2 when we get to it. So let's go to x is equal to 0. When x is equal to 0, well, a half of 0 is still 0, so we're looking for f of 0 from above is 0. When x is equal to 4, we're looking for f of a half of 4, which is equal to f of 2. And looking above, when x is 2, f of 2 is also 2. And when x is 8, f of a half of 8 is equal to f of 4, which is equal to 0. So now we've got the points negative 8, 0, negative 4, negative 4, 0, 0, 4, 2, and 8, 0 on the graph. On our new graph. If I try and connect those, I get something kind of like this. Now notice that the y values are the same as the ones above. 0, negative 4, 0, 2, 0, 0, negative 4, 0, 2, 0. So the y values haven't changed. But again, what has changed is the x values that they correspond to. It used to be negative 4, 0, now it's negative 8, 0. It used to be negative 2, negative 4, now it's negative 4, negative 4. So the x values have doubled while the y values have stayed the same. What that's done to our graph is it's horizontally stretched it by a factor of 2. It's horizontally stretched it by a factor of 2. So the x values have doubled while the y values have stayed the same. Notice again that while this is a half, this number in here, the horizontal stretch factor is actually a 2. Now remember that 1 divided by a half is 2. There are 2 halves in a whole. So again, it looks like we've flipped this upside down in order to get the horizontal stretch factor. So let's take a look at the sort of more general rule. Horizontal stretches occur when you have when you replace x with kx, where k is any number. And again, this k could be represented by another letter, but the textbook that we're using uses a k, so I'm going to use that here. So there's some number in here being multiplied by the x before you plug it into the f function. And that's going to stretch the graph horizontally by a factor of 1 over k. So we had to flip it upside down. When this was a 2, it was a horizontal stretch factor a half. When this was a half, it was a horizontal stretch factor 2. So take a look at these. If this is the parent square root function, this here is being multiplied by a 2, so this is going to be a horizontal stretch factor of a half. Whereas here, it's being multiplied by a half, so this is going to be a horizontal stretch factor 2. Again, a little bit counterintuitive, just like the translations were when we're working in the horizontal dimension. Okay, so horizontal stretches, you have to flip that k value upside down to find the factor. Next, we're going to look at horizontal reflections.